Hey folks, Stat Jackson here. So basically in this exercise what I want to do is just do an ANOVA analysis of variance on basically my family members, and what I want to do is just take their thermometer, their temperature readings, and figure out as a family, do we have all the same the temperature, because we're just being a family. So I've got my two daughters, Emery and Warren, my wife Whitney, and my mother-in-law. So we'll do, and including me, we'll do all that and then put it all together and then be ready to go. All right. All right, so this is the problem here with analysis of variance. What we have is my daughter, person number 1, Warren. These are the 4 readings taken. Person number 2, my other daughter, Emery. These are the 4 thermometer temperatures taken. This is me here, starting out with 96.7 degrees. And then my wife, Whitney, starting out with 96.9 degrees. And then Grandma here, the last one, person number 5 here, starting out with 96.9 degrees. So all 4 of those temperatures are taken where the sample size is the same. So her record here, we'll note that n is equal to 4. Basically, from the null hypothesis, it's important to state that all, on average, despite the sample size, that we will assume that the mean is the same for person number 1, as outlined up there at the top, person number 2, 3, 4, and then person number 5, their population mean is the same. But for the research hypothesis or the alternative hypothesis, we want to try and prove that they're not the same for whatever reason that is. So the null hypothesis, we're assuming that they're the same. We're going to try to prove otherwise. Okay, so starting off with this, we had to collect some statistics for it. So starting off with each one of the persons there, number 1, number 2, number 3. Here we'll note here at, actually I'll put it right here. So for person number 1, we have n, the sample mean, and the sample variance. And each one of those persons will have that recorded. So for Warren, the sample size was 4. Her average temperature, 96.525, and then the standard deviation is, the variance is 0.1225 for person number 2, Emery. Same sample size. The sample mean is 96.7 degrees and 0.0467 for the variance. Number 3, for me, 4 temperatures, 96.75 degrees the average, and 0.03 for the variance. For my wife, sample size is 4, 97.2 degrees and 0.04 for the variance. And then last, for Grandma, 4 temperatures recorded, 97.125, and then the variance was 0.0425. So then what we want to do is figure out setting up for this right distribution. So here, F distribution is right skewed, starting off with 0, and we want this to be right tail. So this is just a generic right skewed. Here would be F naught, and to calculate that, and we'll assume here for a 5% level of significance, which is the same as 0.05. F is figured out to be 3.056. And we want to be beyond that cutoff point for significance. So what we're going to end up doing is figuring out the value for F. So F is equal to n times the variance of the sample means of our X bars divided by the mean, the sample mean of the variances. So gathering all the data up here, I've already done that. So n is equal to 4, and you're going to multiply that times the variance of the sample means. So back up here at the top. So what I did with all these sample means is I found the variance of that, and that was recorded to be 0.0839. Make that a 9 there. And then down here at the bottom, I averaged all those variances. So that mean is equal to 0.0563. So basically, I'm going to divide those two numbers and multiply that times 4. 4 times, again, the variance of the sample means, so the 0.0839 over the average of the sample variances. So 0.0563, multiply that all together, and we get 5.961. So this number is from our data, and it's showing to be in the rejection region here. By the way, calculating the p-value for that, the probability value for that turns out to be 0.0045, or that could be looked at as 0.45%. So that's definitely significant, and that would prove a rejection of the null hypothesis. So we can reject this, and thus proves that our temperatures on average are not all the same. One of the things you could do is a pairwise comparison, figuring that out, like which one to offset that. Basically, looking at the means here, it looked at like my two daughters and myself were about the same, and then my wife and my mother-in-law were a little bit different. So that offset that. But there you go. There's our analysis of variance for temperatures taken for family members.